We have been building these functions, such as our latches and our flip-flops and so forth. And I didn't make this stuff up. I wish I could claim that, yeah, it all came to me in a dream before the semester started, but no, that's not really the way it works. Other people have done this, and I am repeating things. So I am going to come over to Google, and I'm going to search for 7400 series. And if I could type what I'm saying, series. Now, Google knows me well enough. It says, okay, you want to follow that with logic? And I'm saying, yes. It may or may not do that for you, but 7400 series logic either way. And again, Google knows me. First thing I get is a Wikipedia article. That may or may not be your first hit, but I'm assuming that pretty quickly that would come up there. You do notice that there are some other sites like Build Electronics or whatever. List of 7400 series IC pinouts, example circuits, and more. And then there's some pictures of exactly what I have in mind. And you will after this. So it is a real thing. If I come over to the Wikipedia article, it's a list of digital logic integrated circuits, ICs, abbreviated. We used to use that a lot. Now we call them chips. Okay, all the same thing. Back in the 60s, but they're still around and still being used. And then there's some other information here. But what I want to do is come down here. They have a list. And I will gladly field any questions on any of this stuff if you want in Discord. But there's a list of circuits here, and we see that they all start with 74 and then a couple of digits. Now, we call them the 7400 series because when they started this, I don't think they ever anticipated having thousands of variations on it. So it was just 2 digits, 74XX, kind of like that. Well, it turns out that we ended up with a lot more than 100 of them. So it does go on to like 74, 112, and so forth. There's also, they have an X here, and so you might find one or more characters in there. You'll commonly see like 74LS, 2 digits, which has to do with the technology. Don't worry about that right now. On that, but then we see the number of units, which is the number of gates units inside the chip. There's a description here, inputs, outputs, number of pins on the package itself, and then over here in the last column is a data sheet. And you know, these are SN, so you might see some letters before the 74 in there. That's fine. They'll be different based on different manufacturers. And then these are LS, which is a low power version. Don't worry about that. What we've been dealing with, well, I guess if we look at 7400, okay, that's a quad NAND gate. So that means there's 4 NANDs in this one chip. And if we were to come over here and look at the data sheet for it, what we find, oops, I guess I could have done that here, is it starts out with a part number and the company. So this was TI, Texas Instrument. You might recognize that from your calculators if you have a TI-85 or whatever kind of thing on that. But they were a big chip manufacturer before they started making calculators. Anyhow, there'll be a title, a description of it, and then the features. So this is a common format of a data sheet, which is what electronics people would use when they were designing with these things. So it gives us some features, which the features will include not only the internals of the chip, the logic and so forth, but also include things like the packaging, the electronics, the electrical levels and so forth. So you see like package options here. Great. Applications, yeah, whatever they thought it might be used in. Then there's a description. So here you can see that TI like to use Y for the output, where I use Q. They used A and B for the inputs. You remember that whole weird active low thing? that we covered when we got into the NAND gate, with the latch. When we got to the latch, and we built that NAND latch, we had Q was set when the set input was 0, not 1 like we would have expected. And so I used an asterisk. Okay. Well, you can see here in the PDF they can use an overbar. So this means not A, or A is the unpreferred state. Let's see, device information, and then quite often, now some data sheets get pretty skimpy on information, but here they're showing you the symbolic picture. This is the ANSI symbol for a NAND gate, and then table of contents and specifications. So there'll be a lot of electrical information in here and a lot of mechanical information on the packaging, all of which we can probably disregard for our purposes right now. Yeah, then they're showing some package versions of this. So inside of the pin numbers, 1 through 7 on this side, 8 through 14 on the other side. And then pin 1 was the A input of the first NAND gate. Pin 2 is the B input of the first NAND gate. And then 3 is the Y, the Q, the output of the first NAND gate. And then we see that there was the VCC, that's the power for the chip. And then over here will be ground. So those 2 pins provide the power for the chip. And then we see that pins 5, 6, and 7 are the second NAND gate. 8, 9, and 10 are the third NAND gate. And 12, 13, and 14 are the fourth NAND gate on that. So, okay, great. Not much more on that, really. Again, we'll see some electrical information in here, the ratings for the chip, some more electrical stuff, and maybe some environmental stuff, temperature and so forth on that. Okay, great. I didn't mean to do that. That was a fairly simple one, 7400 series. Let's go back here. And if we go down through the list, we see that inverters, that's a NOT gate. So you can get 6 of them in one chip on that. Several variations of quad 2 input. So 4 2 input AND gates. There's 2 different versions. So 8 and 9 were both 4 2 input AND gates on a chip. The outputs were different. That's an electrical thing that I feel like I should probably just skip over, but I can't. Remember in CircuitVerse, we said the rule is you never connect 2 outputs directly together.
Right.
Because, what would happen if one's trying to be a 1, one's trying to be a 0? Well, electronics people had a couple of ways of dealing with this. One of them is this open collector thing. Okay? And so if you have open collector outputs, you can connect them together. Okay. Someday, if you want, I can go into more on that in the electronics and what the heck is this collector thing all about. It's actually it has the transistors in the chip. But for the moment, we'll see that, okay, here are 3 3-input AND gates. So just like we went through and said, okay, what happens? How do we cascade ANDs and NANDs together? There are chips that have done that for us. There's a buffer, so that's the not inverter kind of thing. That's which we said you get the same thing out that you get in, but maybe there's a use for that. Turns out that they are kind of useful. Not as common, but that's available. Then we get into some more ands and nors, and I'm looking down through here. I did want to make sure I didn't skip. I don't think I have yet. But we do get down to BCD. Do you remember binary coded decimal? Okay, well, so we see that here's a BCD, binary coded decimal to decimal decoder for a Nixie tube, which was a display sort of like our 7-segment display. Okay, I guess we click on one. It was a different, it wasn't really an LED. It wasn't 7 LEDs, but it was a different technology. But prior to the proliferation of LEDs, we could use this for a digit display. Then there's a BCD to decimal decoder. Probably if we look at that one. We see, okay, here's the data sheet. 4 lines coming in, so it's basically a 4 to 10 decoder. They give us the pin out here, and then a version of the chip, and then we can actually see some of the logic inside of it. So again, some data sheets are kind of skimpy, but sometimes they give us more information, and we can see the logic inside there, which might actually look kind of familiar. So here are the inputs. They've taken each input and knotted it. Oh, don't worry. They put the, remember we said with an inverter, you knew the symbol because the circle on the output made it an inverter. We said that's the opposite. Well, here they're putting the circle on the input. Again, some other day you can, or in Discord ask me, I can elaborate more on that as to why they would do that. But essentially, it's an inverter, the same. Don't get too hung up on whether that circle's on an input or an output. It simply inverts it. What I wanted to get at, or what I was trying to say is, here's each input and the knotted version of it. And so then we're taking those combinations and NANDing together different combinations. And again, we use multiple input AND gates. They're using NAND, so their final outputs are inverted from ours. Not an uncommon thing in the electronics world, but it just reverses the logic. We know that. We've seen that. Hopefully, we're kind of comfortable with that.
Yes.
Okay. And then we see some more electrical stuff. So this has to do with the inputs and outputs. Again, I can elaborate more on that someday if somebody wants me to, but I'm going to skip over it for the moment. And then, oh, look at this. Glorious. Truth table. Yep. So we're familiar with that. Then we get into some electrical information for it. And some timing information. Let's see. So what we can see here is we said that there's a propagation delay. It takes, for a real circuit, it takes a finite, very small, short, but finite amount of time for the input to actually get to the output. And so we can see that these things, the transition time or propagation time, was on the order of tens of nanoseconds. Pretty quick, but not instantaneous. And then some mechanical stuff, how you could buy them. You could buy individual chips, or you could buy them in a tube. You could buy them on a roll of tape for automatic insertion machines, and blah, blah, blah. Okay, so that was that. I don't know, we haven't talked, did we talk about gray code?
No.
We should.
We did it.
What's that?
We did it, I don't remember.
Okay, I don't know that we did or not. We should one day. It's kind of fun. Essentially, if we did, it would have been when we were going through the combinations for our latches, because we said in a latch, when we evaluated it, since the inputs depended upon the previous outputs, that was when we really got the rule that, okay, whichever input changes, that's the one we have to evaluate first. And the fact then that, again, with that propagation delay and so forth, only one input can change at any instant in time. So, it might look like you're pressing 2 buttons at the same time, but only one of them gets evaluated at a time. Only one can change. So when we're going through the truth table, instead of doing our regular counting of 0, 1, 2, 3, 4, 5, we thought about it in a different order. Because what happens when you go from 1 to 2? 2 bits change. Right? Would it help to see this?
No, I get what you mean.
Okay.
You go from 1 to 2.
Yeah.
Both. The first digit, so to speak.
The ones place and the twos place both change, seemingly at the same time. We're like, I can't allow that. So is there a pattern we could go through where we could hit all the different combinations, but by only changing one at a time? Well, spoiler alert, the answer is yes, and that's what gray code is. Then we see, decoder drivers. So here's our 7-segment display stuff. Then we see that there are some and or invert gates, okay, and some different combinations here. So this is where I don't know if we actually built these into subcircuits, but I feel like I might have said at one point in time that it might be convenient to, because remember, frequently we would AND together a number of combinations. I'm thinking about our general rule for implementing any truth table. You take your inputs and you NOT each one. So we've got all the combinations there. And then we would AND together the combinations we wanted. And if there was more than one, we'd OR them together. So since that's such a common thing, we could have made a couple of ANDs and an OR into a subcircuit. And that's what we're seeing here. So again, because it was so common, there would be different combinations of multiple ANDs and ORs in a chip. I guess it wouldn't hurt to say, let's look at the 52. Yep. Although it's showing me an ugly version. Okay. But what we see here is here's expandable 4-wide OR gates. And it's showing us here, yep, there's the AND gates all ORed together, all in one package. And of course, they're expandable because you can cascade them. Internal electronics of it, and then some other stuff on that. So then let's see, some other things here. And look at that, a JK flip-flop. Master slave flip-flop. It doesn't really matter. I feel like I want to look at a 74, but no, you know what? Let's look at this one. Just pick one. Oh, that's not what I want. That's an ugly thing. Can I please get a... Oh, that's a decade counter. I don't want that yet. And gated positive edge triggered flip flop. Let's take a look. 7470. So what we see here is, I don't know if this internal diagram looks at all familiar or not. I mean, they've kind of combined some logic gates with some transistors here. The important piece is notice how there's a line that crosses from this side over to this side. So this is the output of this AND is coming back to an input of this one. And the output of this one is going back to the input of this one. So that's the latch inside there. In fact, actually, you see this again up here. Okay, so that's where the two latches of the flip-flop are coming from. A little extra logic in here. You'll recall when we were using circuit versus built-in one, they had that preset and asynchronous clear along with the enable. And so that's what some of this other extraneous logic we're seeing here is. So we can get a sense of how that was actually implemented. But for the moment, there they are in the package, description of them, the truth table. This is more of an IEC symbol for it, as opposed to the ANSI symbols that we're used to. Is that it? No, there must be more to this document. Oh. Pages? Maybe? Page? Nope, I'm into a magnitude counter there, so I don't know. Internet Archive, whatever. on that. But there's a flip-flop, and someplace we did see in here, right? Where did we see this? Decade counters. Okay. So dual 4-bit decade or binary counter. So it can count to 10 or it can count to 16 with that. Again, the chip, there's a description of it, and then we see the truth tables. All right. Some internal stuff, and is it going to be nice? No, it's skipping that a page. Oh, because it's 2 pages in one. That's what's going on. Okay. I'm catching on now. So then internal logic diagrams. There are the flip-flops, the clock coming in that is common to them. You see that. And then a couple of variations as to whether it's counting to 10 or counting to 16. I will stop and I'll go over that. We've kind of hinted at it already, because we just said that, oh, with that loadable counter, we could load in a different value. So we could make it so that when it's ready to overflow, when all the outputs are 1, instead of rolling over to 0, it loads in a different value.
Right.
You get the idea. You can play with it, and at some point I'll probably play with it myself and show some examples of that. But for the moment, I think, was there anything else I wanted to do? That's the basic idea behind the data sheets. Again, they give us these pinouts for it. Oh, look at that. There's a RAM. And an adder and some other stuff that we need to look at. Yep. But this would give us the pinouts for these things. If you'll humor me, then I am going to... So what electronics people would do is they would take these layouts and they would put these together on a circuit board, or what we call either a PCB or a PWB, depending upon your preference, as whether you want to call it a printed circuit board or a printed wiring board. Okay, but the basic idea. What's that? Breadboard. So let's see. Google, help me out here. So if I say breadboard, I'm thinking of something like this. Right. Okay, and this was for prototyping, it was for temporary things. So each of these holes you could stick a wire in, and so if you had one of those chips, you could stick it on the breadboard into these holes, and this whole column is one big metal clip behind here. So when you stuck a wire in these holes, they were connected together. And again, this would allow you to connect things together to prototype things, check things out, but it's not very robust because the wires are always falling out and get pulled out or bent around, kind of thing. But once you had the circuit the way you wanted, you knew it worked, then we would create a printed, look at that, printed circuit board. And if I go to images, that's when we see the board like this with the chips on it. Okay, and the connections are permanent. Okay, so here's this. Typically, it would be like a fiberglass material for the board itself. For most common applications, there's some weird materials when we get into high frequency stuff, but it would typically be literally a fiberglass material sheet, and you could get it coated on one or both sides with copper. So a thin layer of copper that would be either deposited on, in other words, evaporated and condensed and deposited onto the board, or rolled onto the board. So high temperature and roll a layer of it on. For our bread, it makes a difference to some people. In some applications, it makes a difference. But anyhow, either way, you get this sheet of fiberglass with a layer of copper on one or both sides of it. And we'd call them either single-sided or double-sided boards. And when you created what we call the artwork for the connections, so we would have to somehow create, and I'll show that in a minute. We'd have to create a mask. We'd have to create, typically on what we call, typically on a mylar, a transparent plastic film, but it would have dark areas and light areas to represent where the copper should be left and where it shouldn't be. Okay? We'd refer that to a mask. We would coat that board. So imagine this entire board has a layer of copper on it. We coat that with a layer of what we call photoresist. Okay? A polymer material that's liquid normally, and we put a thin coating of that on here. Then we put our mask on that. So we put that mylar film that has the dark areas and light areas on there, and then we expose that to ultraviolet light, because the ultraviolet light, the energy in that, would polymerize the photoresist. In other words, connect the molecules together so they were hardened. So when you took the mask off, there were soft areas and hard areas, where the areas that were hot, and you'd wash away the soft liquid photoresist, it was still liquid, and you'd be left with the hardened resist in certain areas. So that then, when we took and exposed that board to a chemical that would eat away the copper, like a ferric chloride, or now there's a newer one, what do we use now? It's not coming to me. But anyhow, a material that would eat away or etch the copper, but it could only do it where it got to it. So those open areas, wherever the photoresist was left behind, that copper would be left. Okay. Undercut a little bit, but don't worry about that at the moment. And then you strip off the photoresist, and you're left with what looks like this, where these lighter areas, the lighter, whiter areas, are actually the copper that's left behind there. The green areas is the green of the fiberglass board underneath. So again, these white areas we call traces are copper wires, thin copper wires on the board. You would then take your integrated circuits, your chips like this, put them on here, and solder those leads. Apply a solder. Are you familiar with welding, brazing, metal connecting?
Oh, yes, I've used soldering in very limited applications.
Oh, okay.
I get what you mean.
Okay. So the difference is welding, we actually melt the base materials, and then they flow together and harden, soften, or harden rather as they cool, kind of thing, and that makes the connection. In soldering, instead of melting the metals, the base metals, we're melting a third metal. It flows in between there. So it's more of a soldering or brazing thing. Okay. We do that, and then that chip is now rigidly connected to the board, as well as electrically connected to these traces, and our circuits are ready to be used. I will note that you'll notice there's holes, like right here there's a little hole, and then you see this thing we call a pad, where a lead from a chip would sit on this pad, and we would solder that. And these holes are actually what we call vias. So in the manufacture of the board, this is for a double-sided board. If it was a single-sided board, that's it. Everything's on one side. But with a double-sided board, what we can do is we can connect the traces on one side to traces on the other with these vias. So after the board was etched, there would just be a solid copper pad here. And then we would have a drill file. So we would drill through each of those, a hole, and then we would plate those. So we would plate the inside of the hole with metal, and so now they were connected together, and we call them plated through holes. or played through vias. And then, if you really wanted to, we could take multiple of these boards and stack them up and create a multi-layer board. Essentially, stack them up and glue them together. So, typically, probably like your motherboards and things in computers that are much more complex boards are probably multi-layer boards. But that's the plated through holes. The vias on that, so we can connect them together. What else can I say about that? Do you have any questions?
No.
Okay. So then, the other thing that I'll show as quickly as I can is typically the way that it starts is an electronics engineer would have an idea for a circuit. And they would come through and they would probably do some breadboarding of the circuit. Let's see. Let me do this here. I was looking for something. Okay. That's kind of simple, but you can see these wires and components stuck in the circuit board. So we do some prototyping, test it out, and then once we were satisfied it was working, we would go to what we call schematic capture. So we would actually draw out the electrical drawing for this thing. So there is an open source program called KiCad that's pretty popular these days. And there forums, yeah. Oops, that's still a forum. I don't want that. I want the official site. Where's their official site? KiCad.info. So, okay, fine. Do it this way. KiCad.info to get to their main site. Okay. Why does it still take me to forum? Defaulted there. Okay. What if I said www? Is it org for the main site? Maybe it is. Okay.
You can get to it from that forum page.
Yeah, I probably just clicked on the header there. Okay. Yeah. Okay. Let's see, where was I going to go with this? So it's an open source program that seems to be fairly popular. There's a bunch of them out there that do this. This whole schematic capture, printed circuit board layout kind of thing like that. So because it's open source, it's free to download and install. I just happened to do that the other day, so I can say KiCad, maybe, and run it. And by the way, I have not used this software except for a little bit the other day playing with it. But what I can tell you is there's a bunch of programs that do this. They're all conceptually the same. It's the user interface that differs from one to another on that. So I just have to learn where things are. But whichever one software you get, there's a schematic editor here. So this is a schematic capture part that I was talking about earlier. And then there's a PC board, printed circuit board editor here to do the layout stuff. And then there's a few other tools. And like Gerber is the format for the layout files and the drill files and stuff. Things like that. But the two, and then there's a symbol editor because we need a library of all the various symbols that we use. Some of them, like the 7400 series, those will be built in. But if you're creating your own black boxes, your own circuits and so forth, and want to reuse them, we can create a library of those as well. So essentially, I'm going to pop into the schematic editor, and it's going to say, oh, yeah. Oh, it did. Okay. I feel like the other day it made me name something and call it something. So if it bugs you for a name, just give it a name, and it'll do its thing. Okay. what it's showing us here is a drawing format. So because these things historically have been printed out on big pieces of paper, on plotters and things, we had all these different drawing sizes. You are probably familiar with letter size paper, 8.5 by 11.
Right.
And so we have different sizes, A, B, C, D, E. They kind of like double. It's kind of like a binary thing. They double in size each time, kind of thing. And so, and then there would be a standard title block. So the title block would, oh, this is user interface thing that Grumble I've got to get used to. Shift, Control, which does which. Okay, so right click is doing pan here apparently. Control, mouse wheel, is scrolling around. Mouse wheel alone looks like it's zooming, kind of thing. So okay, use those controls. Anyhow, I was saying the drawing format. So does anybody remember what we did before we had Google Maps, or you could pull up a map on your phone? Yeah, there were road maps. At the gas station, you'd get this piece of paper that was all folded up, and you could unfold it, and it had all the roads and things on it, kind of markings on it. And on the side, it had these letters and numbers, so you could tell which part of the map to go to, because there'd be an index, and it would say, okay, if you're looking for, I don't know, gas station XYZ, it's in cell D5. And you'd be like, oh, D is down here, 5, that's over here, so it would be in this part of the map. Right. So it's the same idea here. That's what those letters and numbers for, because again, these would be big sheets of paper, and you'd be trying to find something on there. So that's all we would call the format. The title block would have pretty standard stuff like the company that was making this, the date and time, revision numbers, and so forth. Okay. So they're providing that, even though we don't typically print them out as much as we used to, which means there's a whole lost art of folding maps. Do you remember that, Chris? There's a certain way they're folded, and it took you a while. Okay, anyhow. So I'll just say this is a drawing. What's that?
I do have some limited experience with blueprints.
Oh, okay. So yeah, blueprints, same sort of thing. Yeah, if you ever find yourself in, I don't know, architecture or manufacturing or any kind of machine manufacturing environments, we typically have blueprints. Yeah. Which again, there's a precise way to fold them, and people get upset if you don't fold them the right way, and they don't stack up nicely. And okay. So briefly, I've got my format here. What I can do is come over here and say place symbols. So if I click on place symbols, it's going out and it's loading the library of symbols that it has. And eventually it'll pop up here. And so here's a library of all the symbols it has in there. But you'll notice that here's the 7400 series. So let's say we grabbed a, again, don't worry, there's HC, HCT, the different versions of it. I'm looking to see the order they're in. It's a little weird there. Because I want to grab something I recognize. So a 7474, which is a flip-flop, a D flip-flop. So it's got one data input instead of the J and the K, and the clock, and then the outputs, and a set and reset. So yeah, I'm just going to go with that for the moment, and say OK. And so I can place that someplace on here. And then I can say place another symbol here, and let's say this I was going to do a 7404, a NOT gate. I place that here, and then I can connect them together. So I think over here, yeah, let's draw a wire. So I click there, and then I drag it over here and click there, and now those two are connected together. So I can go through and draw a whole schematic of the circuit I want, this way, connecting things together. I can consult the data sheets to know, okay, what pin does what on this, and I connect them together. And I don't know, I haven't done enough, yeah, so KiCad has a simulator. I'm not going to embarrass myself by trying it right now, but we could actually simulate the circuit. So, you know, see what it does. Kind of like Circuitverse does, but we're simulating electronically instead of just logically. Yeah. Once you do that and you're satisfied that it works the way you want, then you can go to a printed circuit board editor. I'm going to try it and probably embarrass myself, but because once you have the schematic with all the pins and stuff on it, it can actually go to a layout editor, bring that data over, and it didn't look like it's brought up a different one. Okay, so this is what I was playing around with the other day with a 40-pin chip on there. So I don't know why I didn't bring over mine, but it should be able to bring over the information from the schematic and put the chips there, and then you have to sort them out, or there are auto routers which will try to figure out the best placement and stuff for you. At any rate, what I'm going to do, I think, is I don't know what this is doing. So I think what I'm going to do is close that and come back over here. So the normal flow would be you do the schematic, do the prototyping, do the testing, and then go to the printed circuit board. But there's no reason why you couldn't reverse engineer something, go backwards and say, okay, I'm going to start with the printed circuit board and then go backwards. Kind of like we're planning to do with the claw machine, because we've got this thing, it's got a circuit board in it. We know how it works, but we don't know how things are connected, and we want to figure that out, kind of that. So why does it keep bringing up this one? Okay, well, I don't know. There's a 40-pin socket here, which would be like on an Intel 8051 chip, integrated circuit that you might use someplace. Come on. So I should be able to do the same sort of thing and say place footprints. So now we're thinking physically instead of logically or electronically. And I'm going to say, what am I going to say here? Package. I'm going to do a 14-pin probably a 14-pin dip. Again, I could elaborate more on these someday if you ever wanted to, but that's good enough for me at the moment. I'm going to say place that. Dip as in dual inline pin. So back when we were looking at the data sheets and it was talking about the packages, it would show us packages that were available. And back in the 80s, when the claw machine was made, kind of thing, chips were commonly available in these dual inline packages. We've now gone to something called surface mount for the most part. Again, someday, if you want, I'll elaborate on that, but for the moment, I'm going to say, okay, I've placed two of these sockets that would represent some chip, like maybe this is my flip-flop and this is my my CPU or something over here. But then I can say route a single track, and again, click over there to select that, and then drag this over here to connect those two pins together. And there we have it. So my thoughts are for the claw machine again, that we've got pictures of the board. We've got the data sheets. Mostly, I think we've got all the data sheets collected on that. And so, from the pictures of the board, we could figure out, okay, there's some kind of 40-pin chip here, and there's an 18-pin chip here, or whatever. Put those sockets on there and start tracing out the connections. So then once we have that information, we could say, okay, if this was a whatever chip and this was a whatever chip, these pins would do this, and they would be connected, and reverse engineer it. So, overview of the whole, electronics process, forwards and backwards, kind of thing on that. Again, all this is completely optional for either course, but if you've got time and want to play with it, great. And I'll always
Take a look at the data sheets when they have a chance.
cool. Yeah, I mean, it's fun stuff. I'll answer any questions I can on it, kind of thing. Like I said, as far as the actual software, I need to learn it myself. But